Okay, so we'll cover a geometric series today. Might not take a full 50 minutes, I don't know. Before I do that, I'll put a definition on the board that I forgot to put on the board yesterday, although we did use it. A partial sum. So this is assuming that we have an infinite series. A partial sum is what you get if you take that infinite series and you clip it off somewhere. So the nth partial sum, it's written like that, as an S with an N in the subscript, is the finite sum from 1 to n of, I guess I better not use n multiple ways, but from k equals 1 to n of a sub k. Just for uniformity, I'll change it there too. And in terms of what we did yesterday, the infinite sum is the limit of the partial sums. And we did do an example with this. We looked at Brandy's series. I just didn't use the partial sum notation. I wrote the sum from 1 to 1, the sum from 1 to 2, the sum from 1 to 3. Let's So S sub 1 is the first term, S sub 2 is the first two terms, S sub 3 is the first three terms, S sub 4 is the first four terms, and I looked at the sequence of partial sums, although I didn't use that phrase. And I looked at the limit as n goes to infinity of this thing, and I said, well, this doesn't have a limit. It's not going anywhere. It's just bouncing between 0 and 1. Ergo, this series diverges. Now, this is how we define convergence. Just like when we're looking at an interval, we define an integral as the limit of partial sums, just like with partial sums, Riemann sums. Just like when we're looking at a derivative, we define the derivative to be the limit of a difference quotient. These definitions don't tend to be super helpful in practice, as you might have figured out by now. I mean, if we have like the sum from 1 to infinity of 1 divided by, again, let me transition from using n to using k. Well, it's fine, as for what the partial sums are. S sub 1 is 1 over 1, which is 1. S sub 2 is 1 over 1 plus 1 over 2. So 1.5. S sub 3 is 1/1 plus 1/2 plus 1/3 is what? I mean, it's 3/2 plus 1/3. That's 9/6 plus 2/6. It's 11/6. And I mean, you can keep going, I can go to Desmos and not Desmos, Wolfram Alpha, and very easily found, S sub 1 million. I can find very big partial sums. But as to the question, are these partial sums approaching a finite number? It's really hard to say. In fact, I'd say it's impossible to just look at partial sums and answer that question. There are just a few exceptions to that, so we're going to hit the exceptions this week. And one of the exceptions, well, a partial exception, is what we call a geometric series. And we don't use partial sums in day-to-day life to analyze geometric series. Instead, we have a result that we learn. But partial sums are going to get us that result. And a geometric series, we can do this a few ways. A geometric series can be written like that. So breaking this open, we start with 1. Then we count up. And because of that infinity symbol up there, we count up forever. And anything, well, almost anything except 0 to the 0th power is 1. So this term goes away. And a geometric series looks like this. It looks like an infinite polynomial in R, essentially. When I was mentioning that this could be written in different ways, sometimes you see geometric series written like that. And I'm just going to use n forever. And the advantage of starting at 0 is that you don't have to have subtraction there. You start with 0. And you wind up with exactly the same series. R to the 0 is once again equal to 1. So you can write it, however, but does the geometric series converge or does it diverge? And we can also ask what the geometric series converges to. That's an anomaly. Most of the time, even if you know that a series converges, you don't have any way of figuring out what the sum is. Because it might just converge to some infinite decimal that you can't write down in any decent way. But Geometric series are the exceptions to this. I think this is a little eccentric, but they sometimes get taught in algebra classes. They're nice enough to do that. And convergence all depends on this R. If the absolute value of R is less than 1, then this thing converges. Otherwise, it diverges. And if it converges, it converges to A divided by 1 minus R. And where this formula comes from, I mean, it's a little trick, but it uses the partial sums. So the partial sum of a geometric series is A plus AR plus AR squared plus AR cubed plus, again, I'm trying to break myself of it, but I'm using N in different ways in different problems. But this is the partial sum. We go up to the nth term and we stop. Or really, I'm lying to you. This is because the first term doesn't have an R in it. This is the first partial sum. This is the second partial sum. This is the third partial sum. So that must be the n plus first partial sum. But the trick is that we take this and it's a finite sum and we can deal with it like we deal with finite sums, and we multiply both sides of this equality by R. And when we multiply A by R, we get AR. And when we multiply AR by R, we get AR squared. And so on. We see that most of these terms are the same. The only difference is that we are now lacking a term at the beginning and we have an additional term at the end. And then the trick is to subtract them, and almost everything vanishes, right? We subtract the ARs and they go away. We subtract the AR squares and they go away. We subtract the AR cubes and they go away. The only thing that manages to remain, this A doesn't have anything under it, so it remains. And then this AR to the n plus 1 doesn't have anything above it. So it remains, but we're subtracting it. So it remains as a negative term. And now we do algebra. S sub n plus 1 times 1 minus R is A times 1 minus R to the n plus 1. I'm factoring something out of both sides. Now I'll divide. And at first blush, you might expect some kind of cancellation here. We've got 1 minus a power of r in the top. We've got 1 minus r below. There's no cancellation, but we can take the limit as n goes to infinity. Remember that that we're taking the limit of partial sums to find infinite series by definition. So A, 1 minus r to the n plus 1, up top, 1 minus r down below. As n goes to infinity, those two terms don't change, so we're just looking at 1 minus r to the n plus 1. And I guess more specifically, we're looking at r to the n plus 1. And as long as the absolute value of r is less than 1, this is going to 0. 1/2 squared is smaller than 1/2. 1/2 cubed is smaller than 1/2 squared, and so on. So if this is going to 0, if that term is going to 0, the entire 1 minus r to the n plus 1 is going to 1, and the limit is a times 1 times 1 minus r is a over 1 minus r. Just like we said should happen. And if the absolute value of r is, well, if it's equal to 1, it's just a kind of messy case. If it's equal to -1, you get some sort of Grandy series like thing. But if it's greater than 1, 1 minus 2, 1 minus 2 squared, 1 minus 2 cubed. This will now go to infinity and the entire thing will converge. So it needs to be less than 1 to make this go to 0. I was going to erase it, but so that's the geometric series. I mean, this is basically the answer to the version of Zeno's paradox that I put on the board yesterday, which, remember that Zeno's paradox was an argument that you could not move from one point to another, because to get from one point to another, you'd have to pass that midpoint, and then you'd have to do something else, and there's always something you have to do first. And I mean, if we think of walking at a constant rate of 1 mile per hour, then these intervals are 1/2, 1/4, 1/8, 1/16, 1/32. And this is a geometric series. And it's geometric because every term is half of the term before it. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is 1/16, and so on. It 1/2 is also A. You know, the first term in this series is 1/2. So we have 1 minus 1/2 divided by 1/2. Again, of course, these 1/2s are different. This 1/2 up here is A. Yes, yes, A. And this 1/2 down here is R. What am I doing? I've got those reversed. But we have the same thing ultimately. We have 1/2 over 1/2, which is 1. So this is a geometric series, it converges, we take all of these times together, and it doesn't matter that there are an infinite number of times, because when we add them all up, the result is 1. That's the what I have, but it's a pretty short lesson. Can I do telescoping series from memory? So telescoping series are, I mean, I can tell you what they are. You sometimes have infinite series where if you look at partial sums, you know, you've got a bunch of things added together. But in the partial sum, a bunch of the terms cancel each other out and collapse down to 0. So you can study the partial sums by just looking at a few terms of them. And that allows you to take a limit when you otherwise couldn't. I'm going to need to find a good example of that. One thing I will do, though, since we have plenty of time, not now. Let's try that again. Wolfram so I made the observation back. That is not what I wanted to share at this moment. I made the observation back here that, you know, using partial sums is I mean, in practice, you can't necessarily find these infinite sums this way, because when you look at partial sums, I mean, you just look at them, and it's not necessarily at all obvious from the partial sums what's going on. And I'd like to, this is actually a very famous series. It has a name. We'll talk more about it when we get to the integral test, so you don't need to learn it at the moment, but it's called the harmonic series. And I'd like to just go to our computer algebra system. and look at a few partial sums. And what I'd really like is the ability to magnify this, which I guess I can. It's not super elegant, but here's the fifth partial sum, about 2.3. And the question is, as this upper term increases, are these partial sums approaching a finite number or not? So let's go from 5 to 50. And now we're at about 4.5, or an inconceivably useless amount of precision, but I'm sure it made someone feel very good to make that happen. So if you're going from 1 to 500, we're still sitting here at about 6. And it's really looking as if this is not, I mean, it's really hard to know because this is increasing. Like when we went from 500 to 5,000, we went from 6 to 9. If we go from 5,000 to 50,000, it will go from 9 to 11. But if we now go up, ooh, there we go. We can get it to about 20. And I mean, with decimal or with this powerful numerical tool, I mean, we might guess that this is not going to some finite number. We keep adding zeros up here. It keeps increasing down here. And that is true. I mean, this is a divergent series. It's a famously slow divergent series. I mean, we're up to whatever this is, hundreds, thousands, millions, billions, 5 trillion, and we've only hit 30 or so. There are series. This we know diverges. We'll prove this in the class. I mean, there are series where it is unknown whether it converges or diverges. Not necessarily series that show up in very fascinating applications. More, here's a mathematical puzzle nobody has been able to solve. But I mean, you know, series just involving things like tangents, involving day-to-day sums, day-to-day expressions, where the convergence is unknown. And I mean, you can see even with this, I mean, how do we know that this isn't asymptotically approaching 100? Maybe the sum is 100 and we just haven't gone far enough to see that. So I again reiterate that we use these partial sums to define these series and define convergence. But in general, if we want to know whether a series converges or diverges, we're not going to be able to approach it with partial sums. We'll have to figure out other strategies. And the next, probably 6 weeks, 7 weeks, we will be looking at, well, first we'll be looking at the strategies, then we'll be looking at what we can do with these things. Your inclination might be to say that that this is a mathematical game. like infinitely bouncing balls or whatever, don't show up in reality thanks to physics. But these infinite series have a lot of very concrete, very powerful applications. They're used to study integrals where we cannot use any of our integration techniques, to pick one example out. And it's still kind of early, but a little less embarrassing. I'll end class now and we'll pick it up tomorrow. And I'm probably going, I'll post an announcement. We're probably going to have to do the integral test on Thursday. It was scheduled for next week, but at the pace we're going, I need to do something Thursday.